We'll move on. All right. So how's my volume right now, Professor?
We can hear you now.
Perfect, perfect. I had some problems in the first one or two. I think it's really speaker discipline that caused the issue. So as was mentioned, my name's Sean Martin, and I'm going to give you today a short little introduction to technology readiness level. It's a very complex topic, and some people make their careers out of determining what it is. I'm going to give it to you from really a top level practitioner's point of view, and hopefully at the end of it, at least it will trigger some thought in you in the future as you're designing things or looking at systems. As was said, I went to UF, graduated in '86, mechanical engineering, prior to the merging with aerospace. Earned a Master of Arts in National Security from the Naval War College in 2000. When I was at UF and even after in professional sense, I found that being a member of ASME and taking a leadership role, an active role, helped me build my leadership skills. And I would recommend that or any other similar professional society for your consideration to participate in. I found it very helpful. When I got out of school 100 years ago, went to work for Southern Bell as a facilities engineer, and I really didn't enjoy that position. So I was able to get a position in Panama City Beach at the Naval Surface Warfare Center in Panama City as an engineer, design engineer. I worked there for 10 years and then was able to transfer down to U.S. Special Operations Command here in Tampa, Florida. And those are a variety of different titles I've had. It doesn't really mean a whole lot. Sorry for the acronym soup there, but I've worked in a variety of capacities in the Acquisition Technology and Logistics Center at SOCOM. So what I'm intending to provide today some basic definitions, why it's important, and a few case study examples that I've run across. So as you probably already know, TRL was a product that, or a process that in the 70s to generate an ability for common understanding amongst the employees there, but also the contractors providing services and goods to NASA. So common definitions, common understandings to really quantify risk, which affects TRL was adopted by DoD some time ago and the Department of Energy as well. And has also been spun out into a variety of other readiness levels, like software readiness levels. They use a very similar type of process, as well as manufacturing readiness levels, et cetera. So it's fairly ubiquitous, not that you've heard of it yet, but we'll move on. This is a slide I lifted out of a Department of Energy's. This is the NASA one-page top-level view of how to define.
So sorry to stop you. We are losing the sound again.
Really? Okay, sorry. How about, is this any better?
Yeah, we can hear. It's very weird. You'll be talking and then it'll cut out for about 10 seconds and then cut back in. So
all right, I'll try better. I think I have a sound pressure microphone in my computer and I have to look right at my computer. So I'll do my best.
Okay.
So level one is basic principles, just basic concept. That's a lot of university level work. Level two and level three, it's all basic university level work, concepts, analytics behind it and such. As you move up into the 4, 5 and so forth, you're actually starting to produce prototypes. And prototypes in lab environment for 4, just key subsystem prototypes. And then in subsystem development and demonstration relevant environment for level 5. Level 6 is now you have the whole system integrated together and testing it in a relevant environment. And that is a big step of complexity and effort to get there. Level 7 is now you're pushing this final development version, no longer a representative model, a more mature prototype into an operational level. A lot of work going between each of those steps and getting to that point. And then 8 is qualifying the item in an operational test and demonstration. And then 9 is really a product, if you will. From a commercial sales point of view, it's kind of like the car you buy at your Ford dealership, for example. This is a different representation of basically the same things without as much definition behind it, but it's there to illustrate really where the university work typically takes place in the spectrum, the TRL spectrum, where industry's at. And then 4, 5, 6, and 7 TRLs is the space spanning between universities and research centers and industry. So again, this is just intended to let you know the difference between universities and industry and what has to go through it, what steps you take. So yeah, that's nice. So why should I care? It's a bit academic, but I'm going to try to go through. I will go through a few case studies with you and try to get the gray matter moving a little bit and have some. So TRLs, technology readiness levels. When you define it, when you determine what it is for a subsystem and or a larger system, it's the subsystems. It's important to help you with trade-off analysis for you to be able to understand your risk of maturing that part with regard to performance, cost, schedule, safety. The other side is really the fundamental thing, and I should have started with this slide first, is TRL is a way for you to define and identify risk from a component maturity, an integration maturity. It could be software. There's a lot of things that when you put them together, it takes a lot of debugging, and you have to be able to identify and understand where your risk is. And again, if you could be a small design engineer, if you will, or you could be the program manager in a big project, but you have to understand how your risk that you're managing affects things like schedule and cost and even safety. Safety is a big one, and I'll get into that in a little bit. So with that, before we get into case studies, do we have any basic questions?
Any questions for anyone? I will comment before anybody jumps in with a question that we are kind of every so often losing the sound again. And I think it is actually the closer you are to the computer, the better it goes. So there you go.
Real close.
Yeah. So any questions from students? And I will kind of give you guys the same reminder that I gave to the previous sections is that if you guys have looked carefully at your final oral presentation requirements, there is actually an expectation that you identify the technology readiness levels of the concepts within all of your subsystems. And so this isn't abstract, right? We're actually going to ask you to do this type of analysis and present and be assessed on it in your final presentations. So if you have questions, either of the kind of the general nature of sort of how to do this, or even more specific questions that are relevant to your projects, Mr. Martin knows a lot more about this than I do, and so he's here, and this is really the opportunity to ask. So please jump in if you have any questions.
Okay, silence I'll take as no question. So I'll move on to some of the case studies. And I think that might generate some questions on the application, if you will. So these are 5 case studies that I've set up for you. One is, and I know 4 of them extremely well because I was in charge of the top 4. Dry combat submersible, biomimicry of body armor, surface planing wet submersible, shock mitigating combatant craft seats, and a Norwegian prototype combatant craft. So this dry combat submersible, the propulsion energy source, is a trade-off analysis that I had to do and weigh through. I was the technical director of this effort. By submersible, some people call it a miniature submarine. But something we built a few years ago, and I was in charge of it. This was built in Plymouth, England. And so I had the job of trying to figure out what is the proper energy source, not proper, what is the most highest performance, least cost, lowest risk energy source that I could put into this submersible. The rest of the submersible is largely assimilation of components that were built off of well-known manufacturing processes. For example, the outer hydrodynamic skin there is a composite fiberglass polyester blend, well-known materials, well-known application, well-known manufacturing process, and so on and so forth. So many of the components were high TRL, well understood. The battery chemistry and the energy source had some issues with being as high of TRL and low risk. So I'll go through it really quickly. The silver zinc is one battery chemistry of choice that we had that's been around from maybe 1960. NASA used it in the Apollo program way back in the day. And for its operational use in spacecraft and then later adopted by us in naval special warfare, under certain applications, well understood, mature, safe, long history of use. But in this application, where we would have it many days underway below the surface of the water, there are some cons to that technology. For example, it has a low operating life cycle, only 25 charge-discharge cycles. It means I have to replace all the cells every 25 uses. But the biggest concern from a safety and performance was the heat management. The heat management of silver zinc batteries, as they discharge, they are exothermic. They give off plenty of heat, and that is very detrimental to the batteries. They can self-destruct if you don't do enough heat management. And this application requires significant heat management. So I hired Battelle Memorial Institute and NSWC Crane to work on the heat management and see if we couldn't bring this TRL-4 up to something that was acceptable, like a 7. Lithium ion, excuse me, it was another battery chemistry that we were working in parallel. And there was a bit of how I was managing my risk as well, is working parallel efforts. So the advantages of lithium ion is great operational life cycles, 250 plus cycles, sometimes more. Low maintenance, potentially low ownership cost. But in this application, we had a battery management system that was very low, 4 or 5, TRL 4 or 5. That's because we're using off-the-shelf battery cells in a very small form factor that's commercially available. But in this application, in managing the batteries, I mean, we had 15,000 pounds of batteries here. There wasn't a battery management system on the market we could buy for this application, so it was developmental, very low TRL. The problem you have with some of these low TRLs, if they were to fail, the subsystem were to fail, some of them are going to fail critically, so catastrophic to the system itself. And some, if they're a minor part, it's a bit of inconvenience. It's a bit of so what. The battery system on board a submarine like that or submersible like this would be catastrophic with a failure. So we had a low TRL, technology readiness level, and we put several $1 million into this effort as well. Fuel cells was an initial consideration, but once we did some analysis, we realized the global fuel logistics challenges were just insurmountable. I don't care if it was for a solid oxide fuel cell with a fuel source of methanol or hydrogen, whatever. It was just too hard to crack. So And the other integration aspect or design challenge we had with there is the fuel cells package very differently than batteries. And so we would have had to build the submersible around the fuel cell. So we threw that out quickly in the analysis, and to mitigate risk, I put millions of dollars into both silver, zinc, and lithium ion. So as it turned out, what turned out to be the most effective was the lithium ion. Very expensive choice, but long life, and also low maintenance, very low maintenance. So again, by understanding where developmental items were or subsystem components, we could understand subsystem TRL levels and what the risk was and where we needed to put our efforts or not. We could walk away from it like we did the fuel cells. So with that, any kind of questions about, I know it's a lot really quickly, but any questions about using TRL, looking at a system and using it to help you make trade-offs? Yeah, probably not. Okay.
I actually have a question.
Sure.
So it sounds like a lot of this is based on your experience using this technology and environment that has been facilitated by your company. Can you say there was like another company that had extensive research with lithium ion batteries and submersibles, but they had like, I don't know, they had like some kind of trademark on their research. Is there a way that you could use their information to rate a certain idea with a higher TRL? Does that question make sense?
Yeah, I think I know where you're going. First, I work for the U.S. government. And so, and we only develop things that the commercial marketplace cannot support, for example, nuclear weapons. We do very few things in-house from a design and development and production point of view, because it's just far too costly. So with this, I actually went through a competitive bid process for vendors from around the world, actually, to build this. And so, yeah, you can make deals with companies any day, a business deal to use their technology, to license it. That's all in your business agreements and so forth. I will give you an example on this. I was trying to negotiate with Tesla early on. They had come together with some of their early on battery management systems for their vehicles that I wanted to look at. And they wouldn't answer my phone calls. I went through a major investor in the company that I happen to know out in Silicon Valley, and he got me an appointment. But unfortunately, the senior vice president over the battery development section just left the company. And so from a business point of view, I was wanting to leverage what I think what you're implying is a proprietary process that Tesla was underway. But after that, his predecessor, or successor, I should say, didn't have an interest in working with us. They were interested in building vehicles. That answer your question?
Yeah, I think so. I guess kind of like my follow-up question in that way is, like, for example, the silver zinc battery, it says your heat management was like a TRL4. But then if you're able to have like a system prototype demonstrated in like an applied environment, say like another company had already done that, you just didn't know about it yet, would you be able to, if you then were to come across that late in the process, would you then change that from a TRL4 to a TRL7, say? Well,
it certainly depends if we adopt it or not. And
you'd have to adopt that exact system.
Yeah, check. It's not a universal TRL across, the universe, so to speak. It's the industrial base. It is the project right in front of you. And so sometimes you aren't always at the pointy end of technology, but in my area, I think we were, because it's just not me in an office. I work with electrochemists, PhDs from the Department of Energy, from the military, and we really had a finger on the pulse on the battery technology. Really had a good set of minds. I just happened to be the belly button in charge. And so, boy, if there's something out there, it wasn't in this country. I'll put it to you that way.
Gotcha. Okay.
Yeah, and the fuel cell, for example, I went to Hamburg, Germany, met with Siemens to talk to them about it. And they even said, no, not a good fit. So.
Gotcha. So that the problem with the fuel cell is like sourcing the nuclear fuel in different like
Well,
countries.
it's not nuclear,
Oh,
but
okay.
yeah, but it is the source. It's the logistics tail for the fuel.
Gotcha.
And also the entire design of the submersible would have to be changed to adopt to the fuel cell requirements. So any subsystem, major subsystem you have in a complex system competes in the trade space, in the design space. And fuel cells compete more aggressively than batteries. So batteries, I can put those in pressure containers. And you can kind of see the bulge along the side there. And those are the bulges in the skin over battery canisters. Fuel cells
Gotcha.
that way, not in the energy density that we needed. It would have had to take a big space on the inside of the what I call the people tank, the pressure vessel. So
Gotcha. Okay.
all these technologies have their share of trade-offs.
Okay. Yeah, that makes sense. Thank you.
Okay. So real quick, I added this. I changed it up a little bit, Professor, before, just as a quick reminder. So when we're talking about TRL 4, yeah, we have key elements demonstrated in laboratory environment. So for example, the battery management system and the heat, the risk mitigation for the lithium ion batteries, yeah. Where we were at initially was demonstrated in a laboratory environment. We were working with General Atomics on that. Do was mature it up the ladder, although it's kind of inverted in the scale there, but we had to mature it up to the point that we could get it to an 8. That took millions of dollars to do that. Make sense? Okay. The next one is a little bit more of a science project. A handful of years ago, I was given a little bit of money and said, what can we do with manufacturing to improve the capabilities of the special operations warfighter? And so what I did is we looked at trying to do biomimicry. Specifically, what we wanted to do is laser scan our operators' torso so that we can make a conformal body armor for them. So a personalized set, if you will. And what we did is we investigated the hammer fist of the mantis shrimp, and that's on your left. And the hammer fist strikes its prey at above Mach 1 speed subsurface, which is pretty darn incredible to think about it. And I've watched videos and they strike it repeatedly at Mach 1+2 and so forth until they break apart the shells of their prey and eat them. But the hammer fist does not disintegrate like the shells that they're pounding do. And so the hypothesis we had is that the layup of the materials that comprise the hammer fist, which is right here in gray, it's a continual radial biasing of the structural fibers, like it's illustrated computer graphically on the left. So our hypothesis was that the shock wave that results from impact, which you will have a nice shock wave, does not propagate through the hammer fist, but actually gets dispersed out a bit radially by the way the fibers are laid in there. So what we did is we worked with not only Oak Ridge National Lab, but Aerojet Rocketdyne, who builds rocket engines, because they have just wonderful, wonderful metallurgy skills and knowledge there. And also we're doing some testing, experimentation with additive manufacture. And we tried to build our own version of the mantis shrimp fist using additive manufacture and process in titanium. So from the outward edge all the way through, we had a stratified density from extremely dense to very no density. And the intent was to direct the shock wave. When a projectile would hit the surface and the shock wave would propagate through, the impedance mismatch, or the speed of sound through the solid, as the solid density change, would disperse the shock wave throughout this honeycomb and would never get to the back face. And the shock wave hitting the back face is what really causes most of the damage in armor, at least body armor. And it worked very well for 9mm ball. Stopped it just fine without any backface deformation. But it was a little science project, proof, very useful, but there was also a high density polymer or polymeric process being developed, and that was much, much less expensive. So on the TRL scale, if you will, what we came up with, really a little demonstrator in lab, maybe we got to a 4 on this. We went beyond analytical, we got to a demonstration in a very controlled environment. Many, many more steps before this on the right-hand side could become a product. This is a proof of principle or prototype. Any questions on that? Make sense? Here's one when I was talking earlier about the criticality of a immature subsystem going bad. This is what can happen. And this is a battery fire. This is a program I was involved with. The original, this is the surface planing wet submersible. The original version was designed by me and 2 other guys when we worked for the Navy years ago. And this is a follow-on effort that I managed when I was at SOCOM, still am at SOCOM. So it's a surface planing craft, as you can see from the lower left-hand photo, and it carries up to 10 people, 8 passengers, 2 crew, and it can carry them for a very long distance over the surface. You can then stop it, flood up the ballast tanks, and submerge it in controlled fashion, and it becomes a wet submersible under the water. The guys have to put on their life support system, scuba gear, whatever, and then it's a wet submersible. On the subsurface propulsion, you can see in the right photos, you can see some of the thrusters. Those are battery-powered thrusters. The battery system was one that we were using lithium-ion batteries, lithium-ion cobalt to be exact for the chemistry. What was not mature, again, was the battery management system. So the application of a commercially available cell caused it to have a very low TRL. Now, those are the same battery cells you can buy today. They're in your laptop and such. They're in a variety of applications. But the application, at this point of view, we had tens of thousands of, in this case, we had about 9,000 battery cells in 3 different pods. And as in this application, we had a very low maturity system for the propulsion. And so what we were doing to mitigate the risk, understanding the risk, we were taking the battery systems and testing in the Navy laboratory on vibration tables, heat sinks and cold chambers and so forth, and charging and discharging, and trying to prove them out at a high enough TRL to insert them into the craft. In the meantime, we were operating the craft subsurface with very high technology, but low performance lead acid batteries. So that was our mitigation strategy. But unfortunately, the batteries got inserted prematurely by long story there. And not the government's decision, but the vendor took the batteries, put them in the boat for a demonstration to a congresswoman. And during recharge of the batteries, it caught fire. And so the criticality of failure for this system is huge. Boat burned up. Actually, the batteries burned right through the bottom of the boat. It was a total loss, total destruction. So point is, when you're looking at TRLs, you have to understand where your weak link is, but you also have to understand the criticality of failure. So if it was just some minor little latch on the boat that was not all that mature, it's a bit of so what. You can update that along the way of the development of the item. But when it's a key element, as the terminology they use with NASA, or critical component, you really have to manage. You have to be able to identify the level of maturity, because that definitely equates to risk. So in this case, it burned the boat to the ground, and 3 years and $3.5 million were down the toilet, or should I say were wasted. And so we were doing our best to manage the risk, and we had identified the risk, the TRL, but still through some things beyond my control, this is what happened. So again, from a TRL point of view, key element, that is the battery management system, the battery system. We were trying to get it to perform in a laboratory environment under vibration tables and
We actually lost the sound there for about 5 or 6 seconds.
Right. What part did you lose the sound? Sorry.
Um, about the last sentence that you said, that the part that I heard was any questions, but what you said before that was missed.
Oh, okay. Okay. Well, I was just saying we were struggling to get it at a level 4, let alone level 5. That's a battery system. And so it was not ready. The battery system was not ready to be demonstrated in a relevant environment. Actually, that would be a level 6 for the entire system, because he kept failing in level 4. And so because the vendor unbeknownst to us, grabbed the battery, inserted them for a political moment with a congresswoman, it failed. It failed because it wasn't ready. So that goes back to the criticality aspect of the component. And again, little nuts and bolt pieces that don't really matter if they fail, because the criticality of failure isn't all that great. It's a bit of so what, but that battery system, big deal. You saw. Lesson learned from me is a hard lesson. This is another project I had. I was in charge for about 7 years of investigating the injury mechanisms to our SEALs and SWCs who drive our combatant craft. We have, probably less so now, a higher than usual injury rate amongst the SEALs and SWCs on our boats. The musculoskeletal injuries were at an alarmingly high rate. So I assembled a team of people to not only understand the musculoskeletal system out of Duke University and University of Virginia and Drexel University, but also start working with naval architects and also measurement people and suspension people and so forth, put together a team. And so one of the manifestations of the work is the seats you see on the left. These are semi-active suspension seats that look pretty darn mature, but they're prototypes. And so it can be a bit misleading, what you see as maturity. They were not optimized for the environment from a corrosion point of view. They had some issues with electromagnetic interference. That is, when the seats were on and operational, it interfered with the radio. So some of those things that get you to the final level of maturity, they weren't there yet, but they look really mature. And so sometimes the looks of things, the appearance of things can fool you. So I got a little video of the prototype seats working in a vessel, rib boat. I think this was off of, I believe this was out in the Gulf of Mexico off of Mobile, Alabama. And the person in the lower front right seat with the t-shirt on, he's actually the lead engineer and president of the company developing the seat. So we always try to encourage the people that build our product to actually use it with us when we can allow it. And this is actually a very comfortable ride, even though it probably doesn't look like it. So normally the guys are leaning up, embraced into a bolster, and their feet on the deck, and it just pounded them horribly. I've got a good friend of mine that's a retired SWC, which is our boat operators, that have had 3 of his vertebrae in his neck fused together and both of his hips replaced, and feels probably about 50. But it just pounds him, a lot of injury. These suspension seats would have helped, but they were never put into production. But for another craft, they were. So, but the effort resulted in a lot of positive things, to include an ASTM standard that was resulting from all this work that was subsequently used to build another combatant craft. So Going back to the TRL little chart there. Now, while it was representative of the deliverable demonstrated in a relevant environment, level 6, even say it was a level 7, it was not fully qualified, if you will, for all the environmental conditions. It was not corrosion proof. It did have EMI, electromagnetic interference issues. So there's more work that had to be done, is my point here. While it looked like a final product, the SEALs thought it was a final product. It wasn't. That it required a little bit more work. Actually took about $1 million more, and it was ready. And then we didn't buy it. Yeah, as I just mentioned, there's a lot of things left to do, even though it looked very mature. Any questions on that? This is the last little case study. This is a prototype special operations craft for the Norwegian Special Operations. And this photo was taken, I don't know, a dozen years ago, perhaps 13 years ago. And the boat was a prototype fabricated with known fabrication techniques, manufacturing techniques, and so forth. Probably worked very well in a boat racing environment, but in a combatant craft environment, in the water conditions, the maneuvering required for their kind of boats, it had a catastrophic failure at sea, and somebody was killed on it. And as a result, and so you look at this as technology readiness level. Well, it goes back to the intended use. So while the Norwegians thought they were getting a cutting edge boat, the intended use of the boat was really a little bit different than the boat's design. So that's a real tough one to kind of work through, because it had a full TRL 8 because it wasn't fully in production. But yet it wasn't suitable for the operational side. So you really have to understand, and when you're starting out in engineering, you won't be faced with those larger topics, if you will. You're gonna be worrying about your own little widget that you're building on a bigger system. But somebody has to be looking at the intended use of the thing. Not that everything's gonna be perfectly safe, but somebody has to look at, is this product, this item, intended for the environment we're going to put it in? And sometimes the answer is no, and sometimes people pay for it with their lives. So there's been kind of minimum questions. We're finishing up a little bit earlier. The main points I was really trying to provide in my short little TRL is just a method of common terms. I will say there are software programs that are used to really help you grind down and fill in a lot more top level ones that NASA put out there. So for very complex systems, you will, or a person can be tracing it all the way through to find out where your weakness is, your lower readiness level is from a technology level. So understand there's far more to it. TRL is really a measure of risk, and what you do with that risk is up to the whoever's leading the effort. So it has to be managed in some sense. You can manage through trade-off analysis, like I showed you earlier. Sometimes you do parallel efforts, and sometimes you decide you're not going to go down that rabbit hole of that risk because you can't manage it adequately, and sometimes you will drop performance because you can't manage the risk properly. And as always, never overlook safety, because if you have a component break or go bad on you that's at a low TRL level and it causes a catastrophic failure, like it did on the one boat fire, it's a bad day. So that's really all I got for you. So I'm open to questions.
Okay, any questions for Mr. Martin?
Thank you, Mr. Martin, for speaking to us. I was just wondering, what's your favorite thing about your job?
About my job, That's a very interesting question, because what I've done is pursued a career that I was on one adventure after another. So in my job, I also work with international, different countries around the world, partner nations, as we call them, with their special operations and developing technology with them. Those suspension seats that I showed you, I'll flip back. These seats, I put one of those seats on a British special boat service boat. And I had some of my engineers go over there, and we instrumented the boat and the people and the seats and all that. Very interesting work. Getting to do things is very interesting. Doing things differently and learning. I've had a career that I've learned, never stopped learning, which I immensely enjoyed. I've also been able to go to Navy dive school. As an engineer, I went through Marine Corps Combat Swimmer School as one of 2 civilians ever to go through that. But my career with the military and the line that I've taken, or sector I've taken, allowed me to do that. So I've gone after adventure and continuous learning.
All right. Any other questions?
Yeah, I got a question. Is there like a level of part that you find there's no real point in doing a TRL analysis on? Like, I imagine like maybe like fasteners, like if you just assume that they're well tested in the environment you would need.
That's a great question, because some of those things you can take for granted, but what we have found in military systems is counterfeit parts, from counterfeit bolts to counterfeit chips in circuitry. And most of it comes out of China. And excuse me, some of the bolts that we've tested that on critical systems, some systems are not critical, but I've got a long history in diving systems, recompression chambers, where the systems are critical and certified. And if you have a failure, people die. We have found that we spend a lot of money to validate sources of components. So it depends on the criticality. Now, if you're building something non-critical, if the failure is not all that consequential, for example, right here in this video, these 4 bolts that hold up the arm and so forth, I wouldn't consider those overly critical in the design. If one of those fails, nobody's dying. A loss of life or even injury, probably not so much. I wouldn't worry about those. But if I was building, for example, go back to that. There are bolts in the pressure hull. You can't see them, but there are bolts that hold in penetrator plates where your cabling goes through, and the piping for your oxygen goes through the pressure hull. Absolutely. We have to know where those bolts came from. We have to know the source. We get documentation for them. It's very expensive, because if we have a counterfeit bolt that goes bad, people could get hurt or die. That makes sense?
Yeah. So just make sure I understand. So instead of maybe like comparing the readiness level, just ensure that you're getting the forged bolt you want instead of like a turned bolt or something that's not going to meet your.
Yeah, no, that's a fair point. And it's not necessarily a TRL, but it's a pedigree. And so if you will, you could equate it to TRL because it's truly been tested to the full strength of the bolt. So it's a counterfeit part. So in a way you could say a TRL, but truly it's a counterfeit part that's never truly been validated that performs to what it needs to.
Gotcha. All right. Yeah, that makes sense. Thank you.
And I will tell you, I had that with a dive system I built for the Marine Corps, actually an O2 charging system many, many years ago for their combat diving rigs and their military free fall bottles for recharging with oxygen. And we're using material called Manel in welding these manifolds up. And we had them tested according to requirements, certification requirements through non-destructive radiological testing. So taking images of them to make sure we had full penetration of the welds. And we started shipping these around the world because it was passing. That vendor was no longer available to support us, so we went to a different vendor to do an additional X-rays of the welds. He came back, or that company came back, said, we got to talk to you. Your welds are garbage. They are not passing spec. They're not full penetration welds. So he came by, a representative of the company came by with his X-ray films. And what we found out is the first company had been fraudulently passing the test. And then we found out that they were under charges from the Nuclear Regulatory Commission. We didn't know that. So now I've got these high pressure, like 3,300 PSI oxygen systems around the world, about 7 of them around the world. It's a big deal because if one of those splits, we're lighting some marine on fire somewhere. And so we had to do a global safety shutdown. We had to recertify our welding processes and so forth. So it's a big deal. So my point is, you can't take it for granted when you're dealing with critical systems.
Gotcha. Yeah, that makes sense. If no one else has one, I got another question for you. What kind of work were you able to do with your diving certification as an engineer with the Navy?
Oh, very good. So I was a certified diver for the Navy for 16 years after that. And we did a lot of technical work out in the Gulf of Mexico. The Navy base that I worked for did largely coastal warfare things. And so what we did a lot is put down mine-like objects in the Gulf for minesweepers to practice on, but also put instrumented mine shapes down there so we could sense, or other people could sense, what's going on as the sweepers went by, looking for signatures of the sweepers and so forth. So there's a lot of technical work going up and down. I did some work for the Marine Corps with a underwater dive propulsion vehicle. I was a test engineer for them. And then some of the other work that I've done, for example, on the boat that burned up. Yeah, that sweet thing. I used to dive on that. So I'd go on board, drive it on the surface, then subsurface. Most important thing it did for me is give me an appreciation for how my customer has to go.
Gotcha. Yeah, that makes sense.
Anybody else?
Any other questions? All right. Well, so we're right at the end of regular class time. We'll I'll thank you for presenting to us and sharing with us your experience and teaching us a bit about technology readiness levels. I'm gonna stop recording here in a second. There we go.